Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into designing Google Maps, the system that powers maps, search, routing, real-time traffic, and navigation for billions of users. We'll cover tile rendering, geospatial indexing, route planning, ETA prediction, points of interest, and the low-level design trade-offs. Whether you're preparing for a senior engineering interview or building geospatial services at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into designing Google Maps, the system that lets billions of users search for places, get turn-by-turn directions, see real-time traffic, and explore the world from their phones. If you have ever wondered how map tiles are rendered, how routes are computed across continents, how ETA predictions stay accurate, or how points of interest are indexed and ranked, this video is for you. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FAANG interview or building geospatial services, let's get into it. Here is the core problem. Billions of users expect a map to load instantly, routes to be accurate, and traffic conditions to update in real time. But behind the scenes, the problem is enormous. The world contains hundreds of millions of roads, buildings, and points of interest. Traffic conditions change every second. Route requests can span cities, countries, or entire continents. A user wants to find a coffee shop near them, navigate to an airport with live traffic, and know whether they will arrive on time. Any delay, wrong turn, or stale ETA erodes trust. The business needs a global mapping platform that precomputes and caches the world, answers location queries in milliseconds, computes optimal routes, predicts ETAs, and keeps points of interest fresh and relevant. Let's walk through the functional requirements. First, the system must render a map by fetching and displaying tiles at multiple zoom levels, from world view down to street level. Second, it must support geocoding and search, so users can type an address or a place name and get ranked results near their location. Third, it must compute routes for driving, walking, cycling, and public transit, considering distance, time, traffic, tolls, and user preferences. Fourth, it must provide turn-by-turn navigation with real-time rerouting when a user misses a turn or traffic changes. Fifth, it must predict accurate ETAs that update as the trip progresses. Sixth, it must index and serve points of interest such as restaurants, gas stations, hotels, and landmarks, with ratings, photos, hours, and relevance ranking. Seventh, it should support offline maps for regions where connectivity is poor. These capabilities make a maps product truly useful. Now the non-functional requirements. Latency is critical. The map must feel instant, so tile loads should be under a few hundred milliseconds and routing responses should be under a second. Availability must be extremely high because navigation is used in safety-critical situations across every time zone. The system must scale globally to serve billions of requests per day from millions of concurrent users. Accuracy matters for routes, ETAs, and search results. A wrong route or late ETA directly hurts the user experience. Data consistency is relaxed by design. Traffic is inherently stale by seconds, and maps are updated incrementally. Cost efficiency is important because storing and serving satellite imagery, road networks, and historical traffic is petabyte scale. And the system must be fault-tolerant, gracefully degrading when a data center or traffic feed fails. Here is the high-level system architecture. On the left, clients include mobile apps, web browsers, embedded car systems, and third-party APIs. Client requests go through a global load balancer and API gateway. Map tile requests are served by a tile content delivery network, backed by object storage and pre-generated raster or vector tiles. Search and geocoding requests hit a geospatial index service backed by inverted indexes and geohash grids. Routing and ETA requests are handled by a routing engine that reads a partitioned road graph from a graph store and combines real-time traffic from a traffic ingestion pipeline. Points of interest are served by a POIS service with its own search and ranking index. Telemetry from clients feeds back into the traffic and ETA systems to improve predictions. The key metrics to memorize: cold. Tile load latency, measured at the 50th and 99th percentile, determines how snappy the map feels. Routing response time, especially for long-distance routes. ETA accuracy, often measured as the mean absolute percentage error between predicted and actual arrival time. Search relevance, the fraction of times the top result is what the user wanted. Route quality, the ratio of suggested route duration to the theoretical optimal route. System uptime and availability across all regions. Map coverage percentage, including roads and addresses. And data freshness, how quickly new roads, traffic incidents, and business closures are reflected. These metrics are what the business and users actually care about. Let's trace the end-to-end user journey. A commuter opens the Google Maps app and types the airport. The search service returns the terminal as the top result. She taps directions and selects driving. The routing engine computes several candidate routes, ranks them by ETA with live traffic, and picks the best one. Turn-by-turn navigation begins, and the client prefetches tiles and voice guidance along the route. Midway, a traffic accident appears ahead, and the ETA service updates the arrival time. The routing engine suggests a faster alternative, the user accepts, and navigation reroutes seamlessly. She arrives within 2 minutes of the predicted ETA. This journey exercises search, routing, traffic, tiles, and ETA in one coherent flow. The core models and algorithms. The map is represented by a tile pyramid, where the world is divided into small square images or vector chunks at zoom levels 0 through 20. The road network is modeled as a weighted directed graph, where nodes are intersections and edges are road segments with distance, speed, and road class attributes. Routing uses algorithms like Dijkstra, A*, or contraction hierarchies to find fast paths. Geohashes or S2 cells encode latitude and longitude into string prefixes for efficient spatial indexing. ETA prediction combines historical average speeds, real-time traffic, and machine learning models that account for time of day, weather, and events. The POI index combines inverted text search with location ranking. Caching, prefetching, and incremental updates keep the system responsive. The key trade-off is freshness versus cost. More frequent updates improve accuracy but explode compute and storage. Now the low-level design deep dive. The tile service pre-generates raster and vector tiles from raw satellite imagery, road data, and building footprints, then caches them in a content delivery network close to users. The routing service stores the road graph in a graph database partitioned by geographic region. It uses contraction hierarchies to pre-process the graph and enable sub-second long-distance queries. The ETA service runs a separate pipeline that ingests GPS traces, road sensors, and incident reports to estimate current speed per road segment, then feeds the routing engine. The search and geocoding service uses geohash-based sharding plus inverted indexes for text, resolving queries like pizza near me into ranked POI results. The POI service stores structured business data, reviews, photos, and hours. Client telemetry flows back through Kafka to improve traffic and detect map errors. For scale, each service is horizontally sharded by geography. Key takeaways for your interview. First, Google Maps is fundamentally a geospatial data and serving problem, so emphasize tiles, spatial indexing, and graph routing. Second, always separate the rendering path from the routing and search paths. They have very different latency, consistency, and storage needs. Third, geohash or S2 cells are the standard way to shard and query location data, so be ready to explain prefix matching and neighbor traversal. Fourth, ETA accuracy is the product of historical baselines, real-time traffic, and machine learning, not just shortest path distance. Fifth, scaling a global map requires heavy caching, regional partitioning, and incremental updates, because you cannot recompute the world on every request. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for Design Google Maps. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on designing Google Maps. We covered the full picture, from map tiles and spatial indexing, through routing engines, ETA services, traffic pipelines, and the low-level design of the geospatial stack. If this video helped you, Please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.